In this video, we are starting section 5.5 on equations with exponential and log functions. Our goals for this section are to recognize when an exponential equation requires logs and when it doesn't need them, and also to recognize when we need to check for extraneous solutions, when we use log properties. Okay, so in this video, I'm going to focus on exponential equations, and in the next video in this section, we'll take a look at equations that have log functions already in them. Okay, so recall that an exponential equation is an equation where we have some exponential functions in it. Like there's some number that's the base, some positive number, and then we have variables in the exponent like we have here. So this is an exponential equation, as is if I change that number on the right to a 15. So we typically try the following if we have an exponential equation. So first, we try to get a common base if there is one. So here's an example. In this equation, I can get a common base because 16 is 2 to a power. It's just 2 to the 4. And if I have 2 to a power equals 2 to a power, well, the powers got to be equal. So setting them equal, we get that x plus 1 is equal to 4. And if I move the 1 over, we get x is 3. All right, that's my answer. So if I can get a common base, I want to try to do that. Okay, if on the other hand there is no common base, then we're going to need to use logs to solve it. Okay, so we've seen this before a little bit, but now we're just revisiting the idea. We need to use logs when there is no common base, and we're trying to solve our exponential equation. So, okay, so one way I can do this is I have this equation in exponential form, so I can transform that to log form. In log form, the base of the exponent becomes the base of the log. I'll get log base 2. And then the input and the output get swapped. So the input of the exponential is x plus 1. The output is 15. So they switch spaces. They switch spots. So 15 is now the input of the log, and x plus 1 is now the output of the log. Okay, and now I'm one step away from isolating the x. I move the 1 over by subtracting it. So that'll give me that log base 2 of 15 minus 1 equals x. Okay, so I got this for x. And the 1, I can't distribute that into the log. That's not a rule. Okay, so that 1 was outside of the log, so it's staying outside of the log when I subtract it. Okay, so again, if there is no common base, and with the 15 and the 2, there is no nice common base with those numbers, then I'm going to use logs to solve it like we just did here. Okay, so let's do some more examples. Let us do some more examples. So in this next equation, I got 2 to the x equals 9 to the x times 30. So I'm going to show two different methods that I could take to solve this equation. In the first one, I'm going to get all the exponential terms on one side. So I can do that by dividing 9 to the x over to the left. So that'll give me this fraction equals 30. And now I can rewrite this left-hand side because both of these terms have the same power. I can write this as one big fraction to the x power, and I put the 2 over 9 inside of that parentheses, right? Because if I'm dividing two things and the whole thing is raised to a power, I am allowed to distribute that power to each one of the terms. So I can distribute a power when I'm dividing two terms like this or when I'm multiplying two terms, but I can't distribute a power when I'm adding or subtracting terms. Okay, so this whole thing equals 30. Okay, now I just have one exponential thing, and it's isolated. And if I look at my 2 over 9 and I look at the 30, well, they don't have a nice common base, so I'm going to use logs. So let's transform this to exponential form. So the double-sided arrow just means I'm about to rewrite it in an equivalent way. So I'll get log, the base of the power becomes the base of the log, so 2 over 9 is the base of the log. And then I switch the input and the output. So 30 is now the input of the log, and x is the output. Okay, and I got it. X is this. X is log base 2 over 9 of 30. All right. Let's talk about one other way I could solve an equation like this. And this is typically the one that most folks will remember from an algebra class if you've taken algebra before in high school, which is I can take log of both sides. We can take a log of both sides. And we talked about this method back in the last section a little bit. So when I take the log of both sides, I could pick whatever log I want. So let's just use ln. Let's use ln. Let's use the natural log on both sides. Doesn't really matter which log I use, but typically we use the most commonly used ones, which are ln and log base 10. Okay, so now I can use some log properties to simplify this. So over here I got an exponent in the log. I can move that out to the front. So I'll get x times ln of 2. On the other side, if I have a log and inside of it two things are being multiplied, I can split it up as ln of the first thing plus ln of the second thing. Right? That was one of our log properties where if I'm adding two logs together, it becomes one log and the insides get multiplied. Well, I'm just using that in reverse. Okay, and now in this log here, well, I can move the power out to the front, and doing that gives me x times ln of 9. All right, so now let's get all the variables on one side. So I'll move this x term to this side by subtracting it. So I get x ln of 2 minus x ln of 9 equals ln of 30. So what taking the log of both sides did for me, why it was helpful is after we use some log properties, it let me get the variable out of the exponent. The variable used to be in the exponent, now it's out of the exponent, and that makes it easier to work with. Okay, so on my left-hand side, well, I see there's an x here in this term, and there's an x in that term, so I can factor it out because it's common. So I'll factor out that x because it's common, and that'll leave me with ln of 2 minus ln of 9 in parentheses. That whole thing equals ln of 30. And now I just want to divide the thing that's in the parentheses. So that gives me x equals ln of 30, that whole thing divided by ln of 2 minus ln of 9. And that is my answer. I got the x isolated at this point. So at first glance, we might be like, wait, that looks really different than the answer that we got the first way. But it turns out these are actually the same if we use change of base. So if you use change of base and you use some log properties, you can convert this first log to this other one, and vice versa. And we saw some examples of that in the last section, how depending on what base of the log we use, our answer could look a little different. But if we use change of base, they end up being the same. Okay, so one important thing that I want to notice about this, let me just move this to the side to give myself some more room here. I'll move this to the side. Is if you use log properties when solving an equation, like we did here, like we use the log property to move the power out to the front, we also use the log property that said, wait, if two things are multiplied in a log, I can split that up as two logs added together. So we actually used a couple of log properties. When we do that, we must check for extraneous solutions at the end. We got to check for extraneous solutions at the end because, as we've seen before, when we use log properties, sometimes what could end up happening is maybe some of the logs are undefined, while on the other side of my log property, maybe it was totally fine. So using log properties can lead to stuff being undefined. So what I need to do when I do my extraneous check is I just got to check to see if my logs are actually defined. Okay, and for a log to be defined, I need the inside of my log. So whatever value I have inside of the log, that's got to be positive. So whatever is inside of the log, whether that's the 2 to the x or whether it's this 9 to the x times 30, when I plug back in for the x's, I need those things inside of the logs to be positive. So my logs are defined. So is this going to happen in our problem when we plug in this complicated looking fraction in for the x? So that might look intimidating, but there's a quick way to tell. And that has to do with the fact that the things that are inside of these logs are really easy to analyze. We got 2 to the x, and there's a 9 to the x inside of the two logs. But 2 to any power or 9 to any power, those are always positive, no matter what the x is. And even when you multiply 9 to the x by another positive number, the 30, that's going to just keep it positive. So as a result, my logs are defined. I didn't even have to plug in this complicated looking thing. I could have just analyzed the fact that, okay, each of these things inside of the log is automatically positive here. So that's kind of nice. That saved me some time. So I'll put a smiley face. So as a result, this answer works. It doesn't make any of the logs undefined. So we are good. So notice that when I do this extraneous check, I didn't actually have to plug it in to both sides and simplify it and make sure that they're both the same, although I could. It turns out the only possible problem I can run into is when you plug it in, are any of the logs undefined? Because if they were undefined, the answer is extraneous. It's not going to work. Okay. All right, let's take a look at another practice problem. So for this one, what if I change the exponent on that 2? What if I make it 2 to the 3x? So it's very similar to the problem that I just did up here. And I could definitely use either approach, rearranging it or taking log on both sides. But this first method seemed a little bit quicker for this problem, so let's do it that way. But if I wanted to, I could definitely do it the other way as well. So I'll move 9 to the x over to the left by dividing it. So I'll get 2 to the 3x divided by 9 to the x. That whole thing equals 30. And before, in the last problem, it was really nice because they had the same power. So I got to rewrite the whole thing as just the fraction, 2 over 9, that whole thing to the x power. But I don't have that here yet. These exponents are not quite the same. But if I look at 2 to the 3x, I can rewrite this. This is the same thing as writing 2 cubed and that whole thing to the x power. Because if I have a power and the whole thing is to another power, well, the powers multiply. And that would give me 3x. Okay. And why is that helpful? Well, 2 to the 3, I know what that is. That is 8. So my numerator is 8 to the x. And my denominator is 9 to the x. This whole thing equals 30. Now I can rewrite that as 8 over 9. That fraction to the x power equals 30. And from here, we're good to transform it to a log form. So in my log form, we'll get log base 8 over 9. And then I swap the input and the output. So the 30 goes in the log and x goes as the output. And now I got x. X is isolated and it equals this. And that's my answer. All right, so nice. So notice again, I'm kind of going quickly through this detail, but in this exponential equation, when I look at the 8 over 9 and I look at the 30, there's no common base. There's no nice common base. And that's why I use logs. If there had been a nice common base, then I would just get the common base like I did in this example to help me solve it. I wouldn't need logs. All right. So let's end this video by taking a look at one final example. So one final example. Okay, so I'm going to up the difficulty here a little bit. So let's take a look at this example. Although we've seen some examples like this in previous videos, so we're getting a little bit more practice with a similar concept. So, okay. So let's talk about this. First, what I want to do is I want to give you an opportunity to try it. So pause the video for about 4 minutes to try this one on your own first. Pause it in 4, 3, 2, 1. Pause it and try it for 4 minutes. All right, so hopefully you did that. Hopefully you paused it and tried it. Let's talk about it together now. So one of the things I'm going to notice is in a couple of these exponents, we have things being added together. So that reminds me of some of our exponent rules. Like I got 2 to the 3x first. And what makes exponents add together? It's if we had like 2 to the 2x times 2 to the 1. So if I'm multiplying two terms like this with the same base, then the exponents add. If I do the same thing with this term, that becomes 2 to the x times 2 to the 3. Okay. So I see 2 to a bunch of different powers, to the x, to the 2x, to the 3x. But what I notice about these is we just did a problem where we rewrote that 2 to the 3x let me write it in the following way. What if I rewrote this as 2 to the x power and that whole thing cubed, right? Because if I have a power to a power, the powers would multiply, and that would give me 3x. That's the same. And if I did that with 2 to the 2x as well, this is 2 to the x, that whole thing getting squared. Okay. And what I really like about this is now I'm starting to see the same expression show up in multiple spots. I see 2 to the x here and here, as well as here. Okay. So that is kind of indicating that maybe let's substitute for it. So I'm going to pick a new variable, like maybe I'll call it y, and let's let y be 2 to the x. And if I plug that in, this first term becomes y cubed. This next term, well, the 2 to the 1 is just 2. And if I plug into here, that gives me y squared. Okay, and then equals 2 cubed is 8. And then 8 is multiplying 2 to the x, which is just y. Okay, so substituting in drastically simplifies my equation. Now I have a much simpler equation to solve. Okay, all right, so how do I go about solving this? So I'll move all the terms to one side. So I'll subtract 8y over. I'll get y cubed plus 2y squared minus 8y. That whole thing equals 0. Now I see that y is common to all the terms, so I can factor that out. And that'll leave me with y squared plus 2y, and then I got minus 8. All right, and that whole thing equals 0. Okay, and now I have this quadratic in this parentheses, and that factors. So I'll have y, and then some number, and then y, and then some number. Okay, so I need two numbers that multiply to -8, and they add to 2. Well, that is plus 4 and minus 2. Okay, so at this point, I got this whole thing factored. It equals 0. So, well, I'm ready to read off my answers. So from this first factor, I get y is 0. From the next one, I get it could be -4. And from the last one, I get that y could be 2. So we're getting 3 possible values for y. I'm not done here because remember the original variable in the problem was x. So I got to use my substitution and plug in my values of y into that. So I got to plug back in. So when I plug back in, I get either, well, 2 to the x could be equal to 0, or 2 to the x could be equal to -4, or 2 to the x could be equal to 2. Okay, let me start with 2 to the x equals 2 because I think that's the simplest. So what would x be here? Well, it's got to be 1. 2 to the 1 is 2. Okay, so nice. What about these other equations? So 2 to what power will be 0, and then 2 to what power ends up being -4? Well, hopefully you're noticing something about both of these. Both of these equations have no solution. Both of these have no solution since if you do 2 to any power x, well, that's always going to be greater than 0. It's always going to be positive. Because like even if I plug in 0 for the exponent, 2 to the 0 is 1. It doesn't equal 0. No matter what I plug in for the exponent, this result will always be greater than 0. So it can't be equal to 0, and it cannot be negative. So both of those have no solution. So overall, the only answer to this problem is just x equals 1. And that is my answer. Okay, one brief thing I want to mention about our extraneous checks before. So we mentioned earlier in the video that, if I'm solving an equation and I use log properties, then I got to check for extraneous solutions. And if I look at this example that I did here, I didn't check for extraneous solutions, even though there was a log in the problem. So how come? The reason for that is we didn't use log properties in this problem, like stuff like bringing the power to the front. We didn't use one of those log properties. All we did was just transformed our exponential equation to log form. And if I'm just transforming it from exponential form to log form, that's not a log property. That's why I didn't need to check for extraneous there. All right, so that is it for this video. In the next video, we're going to focus on solving equations that have a log in them already.